Stan Gibilisco here with a little explanation of a very important distinction which a lot of people overlook in terms of wave phase. I'm referring in particular to a topic covered in my book Teach Yourself Electricity and Electronics, and in the 5th edition, which I have before me right now, this distinction is discussed in Chapter 12, starting on page 204 and extending up through page about 206, 207. It's Chapter 12, talking about phase and AC waves. This, as you may recognize, is a sine wave. Time on the horizontal axis, instantaneous amplitude or voltage on the vertical axis. One complete cycle is like this, so we have two complete cycles shown here in this particular example. I am going to talk about the distinction between phase opposition and a 180-degree shift in phase. Phase opposition means when you have two waves in phase opposition, they are exactly upside down with respect to one another. That is to say, if we flip this wave upside down, we get phase opposition. It means it opposes. Every point on the wave is exactly inverted. Whereas a 180-degree phase shift means that we move the wave ahead or backward in time by 1/2 of a cycle. We displace the wave then on a graph like this. If we displace the wave to the right, it lags in time. If we displace it by 1/2 a cycle to the right, that is a 180-degree phase shift. Remember that a complete cycle of a wave comprises 360 degrees. So let's take this wave, let's make a duplicate, and let's make it look a little bit different. Maybe we'll make it a dotted wave instead of a solid wave, and then what I'm going to do with it is flip it upside down. And then let it start at exactly the same time as the original wave did. Now we have two perfect sine waves in phase opposition. Notice that they cancel each other out at every point in time, so that these two waves, pure sine wave, perfectly shaped, and no DC component, that is to say, it's not displaced positively like that or negatively like that. It doesn't have any DC component. It's perfectly symmetrical. The positive peak and negative peak amplitudes are identical. The frequency is constant, and it's a perfect sine wave. So what we get when we invert this wave like that is two waves that cancel each other out, so that if we combine these two together in the same circuit, we're going to get nothing. We're going to get a 0 voltage. Okay, that's fine. Now, if we shift this wave in phase 180 degrees instead, let's do that. Let's make a duplicate again, and then move that duplicate 1/2 of a cycle to the right. On this graph, that means it will lag the original wave by 180 degrees of phase, and once again I will make this wave dashed so that we can be sure that we know which one is which as we follow along. Now, this part right over here and this part right over here are now irrelevant in this graph. The only part of the graph that really matters to us here now is this portion right there. So only think about what's in that box. Look at the two waves. They're exactly the same situation as we had with phase opposition. They cancel, so that if we combine them in the same circuit, we'll get 0 voltage. So in the case of a pure sine wave with no DC component, phase opposition and a 180-degree phase shift are in fact the very same thing. We get the very same result. That is also true, by the way, with a perfect square wave. A perfect square wave. But those are really just about the only two kinds of waves that you're going to find that have that characteristic. I believe maybe a perfectly triangular wave may also have that property, but most waves don't. So here is an example of what we call a sawtooth wave, also known as a ramp. Notice it ramps up, drops down, ramps up, drops down, ramps up. One complete cycle is from the 0 positive going point to the next 0 positive going point. So once again, I've shown two complete cycles here. Now let's make a duplicate of this. Then I will make it dashed once again as I did before so that we can distinguish between the two. Then I will invert the wave and put it back so it starts at the same time as the original one did. Now we have an example of two waves in phase opposition. Phase opposition. Notice that at every point in time the two waves cancel each other out. So what we will in fact get, if we, maybe I can change the color of this a little bit for you. Make it look a little bit different so that, let's try moss green. Oh, does that look like moss green to you? Now we can tell the two apart a little bit more easily, but we can see that they, in fact, cancel each other out at every point in time, just as it, and any wave, when you take it and invert it like that, if it's symmetrical, if the positive and negative peaks are the same, generally speaking, you're going to get cancellation of the two waves. Well, let's re-invert this wave now, like that, and move it instead 1/2 of a cycle later in time. That is, so that it lags the original wave by 1/2 of a cycle. Notice now, remember now, a complete cycle is from one point to the next identical point in the wave. So 1/2 a cycle is 3 hash marks here. A complete cycle is 6 hash marks. I have moved them now so that they are 180 degrees out of phase. And once again, we would want to only pay attention to the range between this point right here and this point right here. These outside outliers here are irrelevant. We're only thinking about what happens when we've got both waves going at the same time. Notice we do not have the same situation at all as we did before. Now it looks like here we're not going to get cancellation. See, these two at this point, these are not going to cancel, so we're not going to get a 0 wave. We're going to get something else. You can plot them if you like. You can take these points and average them and plot them. It looks kind of, to me, it looks a little bit like maybe we'll get a triangular wave. I'm not really sure, to tell you the truth, but it's clear that these two waves do not cancel each other as they did when we simply inverted the original wave like that. There they cancel. So once again, we need to remember that there is in fact a difference between phase opposition which we see right here. In most cases, with most waves, there is a difference between phase opposition and a 180-degree phase shift, which once again we see if we turn the original wave right side up and move it to the right by a half a cycle, like that. Notice two very different situations in the case of a sawtooth wave. And with irregular waves, lopsided sine waves, that is DC components and things like that, we will always get a situation where they do not in fact represent the same thing. These are not the same. So in general, if anybody ever tells you that phase opposition and a 180-degree phase shift are the very same thing, remember, they aren't. They only are in very specialized cases.